So, we will continue with the propagation process. So, propagation process, we need to propagate this faulty point fault of G to the output Z. So, it will propagate, it will call this propagate fan out free C G. So, G has to be propagated. So, it will see that for propagating G, so it is there is only one fan out. So, naturally we need to consider that point. So, this it will find that this is an OR gate. So, it requires that this H point must be set to 0. So, it will call this justify fan out free routine at C H 0. So, that this H point is set to 0, and that in turn will call this propagate it will in turn call this justify routine. So, that this line B is at 0. So, it can also picked up line D to be equal to 0, but suppose it has picked up line B as the candidate. So, line B as put the value 0, justify to 0. So, that way it is satisfied. Now, this it will propagate. So, then this it is passing through this AND gate or through this OR gate. So, it will call this fan out propagate fan out free C to Z, and that is Z is a primary output. So, naturally this is satisfied. So, then the propagation process ends, and we find the test pattern for testing this particular fault G. Now, we will discuss some more sophisticated test generation algorithms, and the first one in that category is known as D algorithm. So, it can handle arbitrary combinational circuits with internal fan out structure. So, previously whatever technique that we have discussed, so that is true, that can work well if there is no fan out nodes, there are only few fan out nodes, but if it has got a large number of fan outs, then this D algorithm can be used. So, the idea is that it maintains a non-empty D frontier. So, we will define what is a D frontier and try to propagate at least a fault effect to a primary output. So, it will try to propagate some fault effect to some primary output, and as a result in the process it will create some more requirement for justification, and then this initially all circuit nodes are at X except the fault site where the fault effect is placed. So, fault effect is D or D bar. So, D value we can put to the desired fault, so that we can get the complement of that as D bar. So, D frontier. So, these are the two terms that we need to define, D frontier and J frontier. So, in D frontier all gates whose outputs are X, but has at least one D or D bar at the input of the gates. So, that is called a D frontier. So, initially D frontier consists of only one gate, the output of the faulty side, but then it will in at any point of time. So, D frontier will have all those gates whose outputs are X, but at least one D or D bar input is present. Okay. So, that is as if D is going to advance through that point. So, that is why it is called a D frontier. Then we have got J frontier. J frontier are all those gates whose outputs are specified by are not justified by the input assignment. So, the outputs are known, output values are known, but inputs are not yet justified. So, inputs still remain at X. So, that is called J frontier. So, this D frontier and J frontier, so they will be propagated in such a fashion that all the inputs of the circuit gets defined, and the fault gets excited and propagated to the output. So, D frontier in this particular case, you see that this is a gate where we have got this line as D bar, and this is a gate where we have got D as one of the inputs. So, these two gates, so they are at the D frontier. So, because their inputs are either D or D bar, outputs are not yet defined. So, this is a D frontier. So, this D frontier contains these two AND gates. On the other hand, this is a J frontier. So, J frontier we say that input is output is specified, it is 0 or 0, 1 or D, output is specified, but at least some one input is not specified. So, in this for this particular gate none of the inputs are specified, for this gate one input is specified, but the other one is not specified. So, these two gates they form the J frontier. So, basically for J frontier we need to justify, like if we are trying to justify this 0, then we have to see how these X values can be, how these inputs can be set, so that we can get a 0 here. Similarly, this line has to be set to D okay, this output has to be set to D. So, what is required is the to set this x to some value, so that output becomes D. So, in this particular case this x should be set to D, that is true. So, these are the J frontier. So, we have got two things, one is D frontier, another is J frontier. So, what is the D algorithm? So, D algorithm, so it will try to advance fault effects in the D frontier. So, what is required is that any fault that has occurred in the circuit, so that needs to be transported to some primary output through the circuit. So, I need to transport this D to the primary output, and in the process some other nodes are to be set to some values. Okay. So, in to propagate this D to this output, you see that we need a 1 at this point. So, this gate becomes a J frontier gate, because its output is specified, but input is not. Similarly, if you take this, if you once you are at this point, so you see that this is the situation where this B has to be set to 0, this input has to be set to 0, because I want to propagate this D through this. So, this particular gate, its output is specified, but so this is forming a J frontier. Similarly, at this point, so D propagates to primary output, but this Z for the gate Z, again this output is at 1, but input is not yet specified. So, they remain at X. So, these gates, they come to the J frontier. So, basically we are trying to propagate this D frontier to some primary output, and in the process we need to some J frontier gates get created, and those J frontiers are to be justified. So, the D algorithm is like this, that initialize all gates to don't cares, set a fault effect D or D bar on the line with fault F, and insert it into the D frontier. So, the line at which we are trying to test for which we trying to test the fault, so we put that line in the D frontier. So, maybe D or D bar, any value can be put. J frontier is initially null, then it will recursively call this routine. So, D algorithm recursion. So, basically this D algorithm recursion, what it will do is that it will try to propagate this D frontier to the primary output, and in the process justify the J frontier. So, we will see this algorithm. If the result is success, then we print out values of primary inputs, because we have got the fault detected, and if the result is unsuccess, it is not successful, then it is the fault F is declared to be untestable. So, this is the D algorithm recursion. Now, if there is a conflict in any assignment, or the D frontier becomes null, in that case it is a failure. So, if there is any conflicting assignment that is occurring due to this D frontier progress, or this D frontier, there is no path by which this D can be propagated to the output, D frontier set is null set, that means we cannot propagate this fault to some primary output. So, it is a failure case. Second case is that we first propagate the fault effect to a primary output. Some primary outputs are available to which we can propagate the fault. If no fault effect has reached a primary output, then while not all gates in D frontier has been tried, so we try to select a gate and a gate G, and we try to propagate this D frontier through this gate G. So, how can we propagate? So, all unassigned inputs of G they should be set to non-controlling value. So, if it is AND gate, then all the inputs should be set to 1. If it is OR gate, all those inputs should be set to 0. So, like that they should be set to some non-controlling value, and we will add them to the J frontier. So, what we essentially mean is that this is a gate, and this input is at D, and we want to propagate to this point. So, what we are doing, so all these inputs, so they are to be put to 1, they are to be put to 1. So, if this input is coming from say another gate like this, then this gate, what happens is that its inputs are X and output is now becoming equal to 1, specified required output is 1. So, this gate gets added to the J frontier. Similarly, this gate if it is coming from say one AND gate, then this will get added to one J to the J frontier. So, in this way all the unassigned inputs of G, they will be set to non controlling value, and they will be added to the J frontier. and then it will call this routine recursively to do those justifications. And after all, if it returns success, then this will return success, otherwise it will return failure. So, this will happen when the fault effect, no fault effect has propagated to a primary output. So, as soon as a single fault effect propagates to some primary output, so it will come out of this if. So, it will at least one primary output has been found to which the fault effect has propagated. Then we check the J frontier part. So, the J frontier is null, that means we do not need to justify any more primary inputs to justify all those propagation through this propagation of this particular fault to the primary output. So, in that case we are successful, we have got the test pattern. Otherwise, so suppose we have got a gate G which is in the J frontier of the which is in the J frontier. Now, G has not been justified, so we take an unassigned input of G, that is J, and set J equal to 1 and insert J equal to 1 to J frontier. So, we try to put J to be equal to 1 and we try to propagate. So, this will again call the recursive algorithm, D algorithm recursion. So, for the success thing. So, this way it will try, otherwise try the other assignment. So, we try with J equal to 1, if it fails we try with J equal to 0, we reset it to J equal to 0 and then again try out the other possibility. So, if both of them fails, then naturally this particular line cannot be set, this particular J frontier cannot be satisfied. Okay. So, that is a problem. So, it will return a failure. Okay. So, this way this D algorithm recursion will D algorithm works. So, we can better understand it by means of an example. Suppose this is the circuit that we have and we are targeting the fault f stuck at 0. So, this particular point stuck at 0. So, initially all gates are set to all gates are all lines in the circuit, they are set to x, and we place D on line f. So, this D line is this line f is set to D and rest are all x. Next part is to propagate fault effect to Z. So, if we want to propagate fault effect to Z, then what we need to do is that, so this line is D, so this has to propagate through this G. As a result, this this A line has A equal to 1 is added to the J frontier. So, this line A equal to 1 is added to the J frontier, so that this D propagates from F to G. Now, after that this D has to propagate from G to Z, and for G to Z propagation I need the line H to be set to equal to 0. So, that this H equal to 0, so that will be added to J frontier. So, at this point of time we have got A equal to 1 and H equal to 0 as two gates in the J frontier. Now, fault effect has reached the primary output Z. So, we try to justify the entries in the J frontier. Since A is already equal to 1, so and A is primary A is primary input, and so we can very easily set it to directly set it to 1. So, A is already justified. Now, for F to be equal to D, so we have to make this. So, this gate was there in the frontier because its output was D and this is this input was X. So, this was there in the frontier J frontier. So, we have to make it to be we have to justify this. So, we have to justify we have to make D equal to 0. For that we make C equal to 0. So, that way for F equal to D, so we have to do this thing. For H equal to 0, so we can do either E equal to 0 or B equal to 0. So, either of them can be done. So, accordingly, so since C line is already set to be equal to 0, so E equal to 0 is E equal to 0 is already done. So, we have found the test pattern where A is equal to 1, C equal to 0 and B can be do not care. So, that is a test pattern. So, this algorithm could successfully find a test pattern for this particular fault. Now, let us try out another circuit. So, where in this case we are trying to see G stuck at 1. So, G stuck at 1 we want to find out. So, initially, so D frontier is containing H because this gate has got D as input and H has the output is X. So, this D frontier is H, and J frontier is having on this gate is there. So, J frontier will have G equal to D bar. So, this gate has to be justified. So, j frontier is g equal to d bar. Now, if we want to advance this d frontier, that is this g h, if we want to advance, then we have to add f equal to 1 and c equal to 1 to j frontiers. So, f must be equal to 1, so that it propagates through this, and this c equal to 1 has to be set, so that this ultimately propagates through this AND gate. So, they are to be added. So, if we justify every value in the j frontier now in a branch and bound search method that we have discussed previously. So, at the same time we must not make d frontier empty or conflict with other j frontier values. So, that has to be there, otherwise you need to backtrack. So, you see that in this particular case it is not possible to satisfy all those constraints simultaneously. That is, if we want to put say this g equal to this f equal to 1, and that will require that this b has to be equal to 1, then we cannot get a d bar at this point. So, that way justification is not possible. So, in this case there is the conflict will come. So, this g gets stuck at 1, this becomes an untestable fault. Next, we will look into another algorithm which is also a branch and bound technique, which is known as PODEM algorithm. So, this is here the decisions are only on the primary input. So, we do not need to consider any j frontier, only primary inputs are to be considered, and there cannot be any internal conflicts. Okay. So, that way the conflict will occur only at primary input. So, there is no point trying to have a j frontier separately. We can directly remember the primary input that needs to be justified for a particular case. D frontier may still become empty. So, that way if we cannot propagate some fault to the output, so in that case D frontier will become empty. So, will be that way there will be a situation where the test cannot be found, and backtracking will be required. In one case D frontier becomes empty, otherwise if there is no x path from any d or d bar to a primary output. So, x path means a path where all the inputs are, all the lines are at x, so that we can put it to any of our desired values. So, that is the x path. So, decisions to be selected based on a backtrace from the current objective function. So, the d in the circuit has no path of access to any of the primary input. So, here you see there is d if you want to propagate. So, this input is already 0 and this input is already 1. So, this d cannot be propagated to any of the primary outputs. So, that is why there is, I will say that there is no x path from to propagate this d to the primary output. So, d is blocked. So, we generate new objectives. So, what is done is that if the fault is not excited, then we return g v bar. So, we need to, so this is the new objective that we have to justify. So, the line g put a value at v bar. So, if the fault is not excited, if the fault is excited, they already excited, then it will come to this part. So, we find a gate d which is in the d frontier, okay, and g an input of d whose value is x. Then the objective becomes, we have to set this line d to the non controlling value v. So, we find out for depending upon the gate that we have. So, this what is the non controlling value for the gate, and the type of the value that we need to set is v. So, basically what is required is that for gate g we need to put it to a value v. So, this becomes a new objective to be justified. So, the fault is already excited. Now, the fault has to be propagate through the d frontier, and for that propagation, so we need to select, we need to determine a path through which the fault can be propagated, and for that purpose we identify a gate and we identify an input value, the input d whose value is x, and if we set x to that proper value, then that fault will propagate to towards the primary output. So, this is the new justification that we have to do. So, these objectives are to be justified. Now, this to select a decision, so it is like this, that there is a backtrace routine that can be followed. So, I is equal to g, that for the gate for which we want to justify, number of inversions is 0, and if I not equal to primary input, that means in that case I is an input of so this is so I, so the I is modified to be an input of I whose value is x. So we take up one of the inputs whose value is actually x now, so that becomes a new I. So if I is an inverted gate type, then number of inversion is incremented by 1. So this way it goes on and end while, and the number of inversion is odd, then V equal to V bar. So basically what we are trying to do is, for a particular input we are trying to see how can we reach a primary input corresponding to that. So if the primary input can be reached by a number of inverted gates, then we can say that number of inversions may be odd or it may be even. If number of inversions is odd, then we need to set the complement of the value, and if the number of inversions is even, then we need to set the same value. Okay. So if number of inversion is odd, then V equal to V bar, otherwise it will be V. So basically for justifying this I input to some value, we need to justify this thing. So I to V. So this I is a primary input. So we need to justify this primary input to this value. So this is an example. So here we targeted fault is f stuck at 0. So for f stuck at 0, the first objective is f equal to 1, because to excite the target fault we need to first generate this particular target, that f equal to 1. Now for f equal to 1, we need to backtrace from the object c equal to 0. So that has to be, we have to backtrace. So we simulate c equal to 0. So simulate c equal to 0, so that will have d frontier to be equal to g, because now this line is at d. So this is d frontier is this g, and some gates have been assigned. So since this is g, the c, d, e and h, so they are all set to 0, and f has been set to be d. Now another objective is to advance d frontier. For that advancing this d frontier, I have to set a to be equal to 1, and we backtrace the object from the object a equal to 1. So if we simulate a equal to 0, and that way the fault is detected at line z. Another example may be like this, that first objective is to excite the fault b stuck at 0 you want to detect. So we have to excite the fault b equal to 1. So we backtrace from the objective. So that is from this objective we backtrace, and we get a equal to 0. So this is the objective that we want to excite, put b equal to 1, and when we backtrace to the primary input, we find that a has to be set to be equal to 0. Then we simulate a equal to 0. With a equal to 0 we simulate, and accordingly we find that b is getting d, c is equal to 0 and d equal to 0, and then the d frontier becomes empty. So we must backtrack. Then backtracking will change a to be equal to 1. So this was the previous objective. We see that with this we cannot achieve the thing, the d could not be propagated. So we backtrack and change the decision a equal to 1. Now we simulate with a equal to 1, and we see that b equal to 0, c equal to 1 and d equal to 1. So but in that case d frontier is still empty, because this d could not propagate to the primary output, but there is no more decision to be simulated. Okay. So this fault is an untestable fault. So another extension of this PODEM algorithm is the fan algorithm. So this is fan is a much more improved ATPG. So it actually uses some concept known as headlines. So headlines are used to reduce the number of decisions and multiple objectives to reduce later conflicts. So what is a headline? So headline is nothing but a fan out free cone. So this is a fan out free cone. So this outputs this particular portion. So this x is, this is a fan out free cone, and we have got this y also another fan out free cone. So these are the fan out free cones x and y. So what is required is that when we are backtracking, so we need to backtrace only up to the headlines, because once we are here, so we know that this is a combinational logic. So this can always be set to the desired value. So this way we can say that okay, this is this can always be simulated to the desired value. Similarly, since this is a headline, so we can so we can continue and come to this point. So, this way we can simulate only. So, whenever we are doing a back trace, so if we find that we have reached a headline, so we do not need to back trace further. So, this is the idea of this fan algorithm. So, we will continue in the next class.